Okay, so we're continuing on our review, and we're working on y prime equals f of ty, right? And we're thinking about graphical analysis. In the last video, we summarized, the technique of, finding a solution analytically. Analytic solution. By that I mean you determine if your differential equation is linear, if it's separable, or if it's exact, and then use a technique to solve, right? Um, so today we're going to focus on this one, graphical analysis. So the general case is pretty simple. General case has to do with the direction field. Direction field. Geez. Field. Okay, so when you're drawing a direction field, right, the idea is that if you're at a point t naught y naught, you can plug that number into your function to determine a slope, and your function must behave in a similar way. So this would be an example of like a slope 1, right? And so I know my function is going in that direction, and so on. So the trick on these is to be able to draw isoclines, and isoclines are curves where the slopes are constant, right? So y prime is set constant. So you could use the 0 isocline, right? The 1 isocline, 2 isocline, plus or minus. You probably wouldn't do too much more than that by hand, right? And then you could draw those curves. So that's the general case. To be more specific, we have the main class for these is y prime equals f of y. Okay, do you remember what that's called? Starts with an A. Autonomous. The word autonomous is there because we don't have an explicit dependence on time, although remember that this is dy over dt, right? So the derivative does depend on time, but it's not explicitly in our formula. Geometrically, right? What does that mean? Geometrically, we know that isoclines are horizontal lines. So this is what we mean by the slopes not depending on time. They just depend on which y value you're at. Good. So we also know that because of that, autonomous differential equations are always increasing, always decreasing, or constant. Never periodic. By that I mean you can't have a solution that does that. In fact, you can really say it's never a mixture of these, right? Periodic is kind of an extreme case, but the reason this is not possible is because that, right? What does that mean? Can you tell geometrically? Yeah, the same y produced two different slopes. Can that happen here? No, it cannot. Okay. Okay, so what are we doing now? The reason this is kind of a nice class of differential equations is because we have a new plot possible, y versus y prime, right? Because, and then we just put our f of y here because of our dependence on, our singular dependence on y. We don't depend on t. Okay. Now from this graph, you should be able to identify equilibrium. Identify equilibrium. Classify equilibrium. Look for where, or identify, maybe I should say, identify where the solution y is increasing and decreasing, and identify where y is concave up, concave down. Okay, so let's go through these briefly. Equilibria are where the function crosses the axis there. Okay, so for example, if this is -2, 1, and 2, maybe, our equilibrium solutions would be y equals -2, y equals 1, y equals 2. Good. Classify equilibria. How would we do that? Well, on this picture, remember that we can draw little arrows, and I would recommend doing that because it helps immediately identify which ones are stable and which ones are unstable. So this is an unstable equilibrium. Pretty clearly, solutions are moving away from it. And this one is asymptotically stable, or we also call this a sink and this a source. This is be another source because local solutions are moving away. Okay. Y is increasing, decreasing. Where y prime is positive, y is increasing. So therefore, for example, y is increasing on where y is in the interval from -2 to 1. Good. It's kind of weird to say this, right? Because usually we say y is increasing and then we give a value of t. But in this case, yeah, the t doesn't matter. We're just giving y's. Okay. The last one is, oh, by the way, if y prime is negative, right, then y is decreasing. Where is y concave up or down? It can be a little tricky, right? We take the second derivative. Oh, let me put down the first derivative first. dy over dt is equal to f of y. So how do you take the second derivative? Second derivative would be df over dy times dy over dt. What did I just do? Chain rule. Chain rule. And now, if I were to do this geometrically, right, this is the local slope in the y prime plane, right? Oops, I'm getting off my page again. And then this is y prime, or f of y, in the y prime plane. So for example, suppose I've got part of my function that looks like this. Oh, let's keep going, I guess. Then in this region right here, right, we would say that df over dy is negative, but then f of y is also negative. So overall, concave up, because we're multiplying those two numbers together. Okay, in this region right here, I'm running out of space. Let me put it here. df over dy is positive because the function is increasing, but the function itself is negative. F is negative. So overall, then we would have concave down in the graph. Okay, and similarly, you could say that this region right here, both are positive, so concave up. Okay, so then we should be able to translate this information to the direction field. This is the y prime plane, by the way. So how would you do that? Well, in this case, I've got the two equilibrium solutions. One maybe here, and one, this one will be up here. These are decreasing function or decreasing solutions. So my solutions are decreasing from here and approaching. Whoops! I didn't want to say that yet. This is concave down up here. Concave down. This is concave up. Right, that corresponds to these two little regions here. And then this is concave up here, right? And this is concave up and increasing. So these solutions are looking like that. And so notice there is a nice change in concavity. Whoops, here, concave down, decreasing, concave up, and so on. Okay, good. And so that's how you draw those. Good. So that is our that is a quick summary of the first part of the course. So try a few problems. I think the best way to do this is just to try a few sample problems and take a quick look at the solutions. Now, because our exam is going to be open book, open notes, I'm not going to provide a lot of reasons for the solutions on the solution set. I'm just going to be writing down the solutions. Okay, so if you do have questions, you can send me an email or talk to me at some point. Okay, I'll talk to you later.